We all have this picture, right? A black hole. You fall in, you get crushed, gone. Simple.
Well, it seems simple, but when you actually look at the physics, that picture starts to fall apart pretty quickly.
Yeah, it dissolves into this huge puzzle. A real clash of the titans, physics-wise.
Exactly. We're diving into the black hole information paradox today. It's where Einstein's theory of general relativity just fundamentally disagrees with quantum mechanics.
Okay, so general relativity,
Mm.
that's gravity, space-time, the big stuff.
Right, and it tells us about the event horizon of a black hole, that point of no return. Once you cross it, gravity wins. Everything, including you, all the information about you, just gets pulled to the singularity and poof, seemingly gone.
Poof. Like hitting delete on the universe. It's an absolute boundary. No way back.
That's the general relativity view. A smooth crossing, then oblivion. But quantum mechanics, it doesn't like that poof.
Why not? What's the issue?
Because quantum mechanics, our rulebook for the tiny stuff, insists that information can't just be deleted, ever. It can get scrambled, hidden, maybe transformed, but fundamentally it has to still be somewhere.
Ah, so that's the core conflict.
Precisely. And our mission in this deep dive is to unpack that, and especially to look at one really wild proposed solution, the firewall hypothesis. We've got some great sources that really explore this.
Okay, so quantum mechanics needs information to survive. Black holes seem to destroy it. How does that play out? Explain the paradox itself a bit more.
Well, quantum mechanics relies heavily on something called unitarity. You can think of it like perfect bookkeeping. Every quantum process should theoretically be reversible. You can run the clock backwards and recover the starting point. Information isn't lost.
Okay, like cosmic undo function.
Kind of, yeah. But if a black hole truly destroys information at the singularity, that breaks unitarity. It means the quantum rules we rely on just stop working there. Stephen Hawking really flagged this back in '76. His paper pointed out this potential breakdown, this loss of predictability, which is a huge problem for physics.
Right, information can't just vanish into thin air, quantumly speaking. But black holes look like perfect information destroyers, which brings us to Hawking radiation, doesn't it? What even is that?
Yeah, that was another huge twist from Hawking back in 1974. He showed that black holes aren't completely black. Because of quantum effects right near the edge, the event horizon, they actually emit a faint radiation, like a very slow leak.
Okay, they leak. But what do they leak? Does that carry the information?
Ah, that's the problem. The radiation seems purely thermal, meaning it only depends on the black hole's overall properties, its mass, its spin, its charge. It doesn't seem to contain any specific details about, say, the star that collapsed to form it or that unlucky spaceship that fell in later. It's generic.
So the black hole leaks energy, gets smaller, eventually evaporates completely.
Exact.
But the radiation coming out is just random heat. It doesn't tell us what went in. So when the black hole is gone, the information is gone, too.
That's precisely the paradox. The evaporation seems to finalize the information loss. And this left physicists with, well, some really uncomfortable choices.
Like what?
Basically 3 options, none of them great. 1, information really is lost, which means quantum mechanics needs a fundamental rewrite. 2, the information is somehow hidden in the Hawking radiation, but in a way we just don't understand yet, maybe incredibly scrambled. Or 3,
Go on.
Something very, very strange happens right at the event horizon itself, not the smooth passage Einstein predicted.
And that's where the firewall comes in. Because firewall does not sound smooth or gentle.
Not at all. This was proposed in 2012 by Almeri, Marov, Polchinski, and Sully, the AMPS team. It's a radical idea. They suggested that maybe the event horizon isn't this peaceful boundary. Maybe it's a region of incredibly high-energy quanta, a literal wall of fire.
A wall of fire? So if you fall in...
You'd be instantly incinerated, vaporized. No gentle journey to the singularity, just bam, firewall.
They laid out the arguments in a 2013 paper.
Whoa, okay, hold on. That completely contradicts Einstein's equivalence principle, right?
Yeah.
The idea that falling should feel like, well, just falling. Locally, gravity should feel like acceleration. You shouldn't feel anything special at the horizon.
We're absolutely right. It's a direct challenge. Einstein's principle implies a smooth crossing. A firewall means an incredibly violent, non-smooth experience. It suggests general relativity breaks down right there, at the horizon, not just deep inside at the singularity. It messes with our whole idea of space-time being continuous.
Man, that feels like tearing up the rule book. But before firewalls, wasn't there another attempt to patch things up? Something called complementarity.
Yes, exactly. Black hole complementarity. That was an earlier, very clever idea. Folks like Leonard Susskind were key players there. The basic thought was, maybe reality depends on your perspective. Well, for someone outside the black hole, maybe the information never truly crosses the horizon. Maybe it gets kind of imprinted or reflected near the edge, scrambled up, and eventually comes back out in the Hawking radiation.
Okay, so the outside observer sees information escape.
Right. But for someone actually falling in, they just pass smoothly through the horizon, no drama, heading towards the singularity, just like general relativity says. Complementarity argued both views could be true, just not accessible to the same observer.
So two realities, kind of,
Hmm.
depends on where you stand. But the AMPS team, the firewall people, they found a problem with that too.
They did. They argued that complementarity, when you dig into the quantum details, actually leads to a contradiction. Specifically, it seemed to violate the rules of quantum entanglement in a way that would break unitarity, that information preservation rule again. You couldn't simultaneously have a smooth horizon for the infaller and have the information correctly encoded in the outgoing radiation for the outsider without breaking fundamental quantum laws about how entanglement works.
So maintaining consistency forced them towards something drastic, like the firewall.
That's the essence of their argument. To save unitarity, maybe you have to sacrifice the smooth horizon.
Okay, firewalls are pretty extreme.
Hmm.
Are there any other contenders? Less fiery options, maybe?
Oh, absolutely. Physics hasn't settled on firewalls by any means. There are other fascinating ideas out there. One big one is called ER-EPR.
ER equals EPR. What does that stand for?
It connects Einstein-Rosen bridges, that's the ER part, basically theoretical wormholes with quantum entanglement. The EPR part, named after Einstein, Podolsky, and Rosen, proposed by Mendocino and Susskind.
Okay, wormholes and entanglement. How do they connect?
The idea is that maybe entangled particles, even far apart, are secretly connected by these tiny, non-traversable wormholes. So perhaps the Hawking radiation leaving the black hole isn't truly separate from the inside. Maybe it's connected non-locally through these ER bridges to the stuff that fell in. It's a very abstract connection.
Well, okay, that's definitely abstract. A connection through space-time tunnels.
Right.
What else is on the table?
Another major concept, coming more from string theory, is the holographic principle.
Holographic, like on a credit card.
Sort of, in principle. The idea is that all the information needed to describe a volume of space, like the inside of a black hole, can actually be fully encoded on its boundary surface, like a 3D image stored on a 2D hologram.
So everything about the black hole's interior is somehow written on the event horizon itself.
That's the gist. All of that 3D information somehow squashed onto the 2D surface. If that's true, maybe information never truly gets lost inside because it's always represented on the boundary.
Hard to picture, but intriguing. Any others?
There's also the idea of soft hair, proposed by Hawking again, with Perry and Strominger later on.
Soft air. On a black hole.
Metaphorically speaking. The idea is that black holes might have subtle, very low-energy quantum fields or excitations, the soft hair lingering around the event horizon. And maybe these could carry the information about what fell in, subtly encoding it and allowing it to escape eventually. Less dramatic than a firewall, more like a faint memory imprinted on the horizon.
Okay, so we have firewalls, wormhole connections, holograms, soft hair. Where do things actually stand now? Do we know which, if any, is right?
Honestly, no. We're still deep in theoretical territory. As our sources point out, we haven't even directly detected Hawking radiation yet. It's predicted to be incredibly faint for astrophysical black holes, let alone probe the fine structure of an event horizon to see if it's fiery or smooth or hairy.
Right, and we still lack that unified theory, the quantum gravity one.
That's the biggest hurdle. We need a theory that properly merges general relativity and quantum mechanics to definitively describe these extreme situations. That's the holy grail that could potentially resolve the paradox.
So the search continues.
Very much so. Researchers are pushing hard in string theory, loop quantum gravity, studying black hole thermodynamics, and experimentally, things like LIGO detecting gravitational waves, the Event Horizon Telescope imaging black hole shadows, even advances in quantum computing and information labs, they all offer potential, maybe indirect clues down the line.
It feels like cracking this firewall paradox, or the information paradox generally, could be a huge key.
It really could. It might unlock that unified theory and fundamentally change how we understand gravity, quantum mechanics, and maybe even space-time itself.
So the big question remains hanging there. Is that event horizon a smooth gateway, as Einstein thought? Or is it a violent firewall? Is information lost, scrambled, or saved in some way we haven't figured out yet?
Exactly. And as you think about that, consider this. Could figuring out this puzzle about black holes, these incredibly extreme objects, actually force us to rethink the very nature of reality? Could it be the key to finally connecting the world of the very small, the quantum, with the universe of the very large, the cosmos?